Today we're going to begin our look into binomial expansions. So what is a binomial expansion? Well, binomial is simply an expression which contains two terms, bi meaning two. So the most simplest binomial expansion would be 1 plus x to the power of 0. Anything to the power of 0 is equal to 1. 1 plus x to the power of 1, of course, would be 1 plus x. 1 plus x squared will be 1 plus 2x plus 1x squared. We've also seen 1 plus x cubed, but if you forget how to find it, simply multiply 1 plus x squared with 1 plus x. And we end up with 1 plus 3x squared plus x cubed. Then we can multiply that 1 by 1 plus x to get 1 plus x to the power of 4. Tidying everything up, we end up with 1 plus 4x plus 6x squared plus 4x cubed plus x to the power of 4. A pattern, if you just look at the coefficients, is emerging. Now this pattern, Blaise Pascal saw the pattern as well, but he wasn't the first. I mean, there's evidence from ancient civilizations, the Chinese, the Aztecs. I mean, there's lots of evidence that these ancient cultures knew about this pattern. The reason we call it Pascal's triangle is because of the relationships that Pascal found within the triangle. He discovered a lot of these relationships. So what is the triangle? Well, 1 sits at the top of it. And then we write the binomial coefficients out in this order. So it looks like a triangle. Then it went 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Now that's where we got up to. But perhaps you can now see the pattern. Every number is obtained by adding the two numbers immediately above it. So 1 plus x to the power of 5. The coefficients would go 1, 5, 10, 10, 5, 1. Then 1, 6, 15, 20, 15, 6, 1. And we can keep going. 1, 7, 21, 35, 35, 21, 7, 1. Then we get 1 plus x to the power of 8. Keep going. There's 9. Which of course brings me to my personal favourite, 1 plus x to the power of 10. The reason it's my personal favourite is just have a look at those coefficients. They're just so nice. 120, 210, first two digits swap around. Then in the middle you get 252, which is a palindrome. It's just so much nice maths there. So as I say, that's my personal favourite. Keep going. There's 11. And we can also create 12. And, well, it's up to you how far you go. We might just stop there with the expansion of 1 plus x to the power of 12. But knowing this triangle can save us a lot of time when it comes to expanding out our binomials. So if I now have a question like this, 1 plus 2x on 3 to the power of 7, all I have to remember is the binomial coefficients. And if I don't remember them, I draw up the triangle. So we would end up with the coefficients went 1, 7, 21, 35, 35, 21, 7, and 1. And then each of those terms, we just play with the powers. So we start with the first number, which was 1, and it'll go to the power of 7. Then it'll go to the power of 6, then 5, then 4, and so it counts down. The other term counts up, starting with to the power of 0. At any point, you can look at a term, and you'll see that those two powers add up to give the overall power, in this case, 7. Well, let's tidy all that up. And there it is in all its glory. 1 plus 14x on 3 plus 84x squared on 9, 280x cubed on 27, and so on. We could also use our binomials to find calculations. Let's imagine we'd lost our calculator and we wanted to find 0.998 to the power of 10 to 8 decimal places. Well, it's told me to use the expansion of 1 minus x to the power of 10. So let's write that down. There's my favourite line. So 1, 10, 45, 120, 210, 252, 210, 120, 45, 10. Now, the 1 will go up in the powers. Negative 1, or negative x rather, will go down. So we see the alternating pattern of plus minus there. Well, 0.998, I could rewrite as 1 minus 0.002. So if I substitute in 0.002 for x, but here's the thing, because I'm doing it to 8 decimal places, I don't need to use the whole expansion. I can stop at x cubed, because after that, to 8 decimal places, 0.002 to the power of 4, for instance, will be 0. Then you multiply by 0 and you get 0. And so every term after that, to 8 decimal places, would be 0. So I really only need these ones here. We can get that that is 0.9801794. We have to find the coefficient of x squared in this expansion. Well, let's expand out the right-hand side. Now, the power of 4 went, the binomial coefficients, 1, 4, 6, 4, 1. Powers of 4 will go down, so we get 4 to the power of 4, 4 cubed, 4 squared, and so on. Powers of 5x go up. So we end up with, well, power of 0, but then 5x, 5x squared, 5x cubed, and so on. But I didn't actually need to write the whole thing out, because we were only interested in the coefficient of x squared. So I know that in the first parentheses 2 would have to be multiplied by the term that has x squared. 6, 4 squared, 5x squared. I really only need that one. And minus 3x, well, that would have to be multiplied by the term in the second one that just has x to the power of 1. X times x gives me x squared. So I really only needed those two. So I could have stopped once I got the 5x squared. I didn't need the other two terms. So the coefficient of x squared, well, the first one would end up with 2 times 6 times 4 squared times 5 squared. And the second one gives me minus 3 times 4 cubed times 5. And we end up with 960. So there's an initial look at binomial expansions. So 15a, we're going to use these ideas. Question 1 we actually did do in theory, but I've written it down there for you.